Good morning. So I'm out again today. I'm up presenting. Thanks for those who sent the notes and stuff. I'll let you know on Friday how it went. So I'm filling in the next lesson 6.3. It's section 6.3 in the textbook, but it's at least those ideas. Arcs and angles. We know what a central angle is. We talked about it last class. So a central angle is an angle in a circle that has its vertex at the center. We also defined or talked about let's find a better color. Let's go purple. An inscribed angle is an angle that has its vertex on the circle. So this next idea, and if you're keeping numbers for this textbook, it would be Conjecture 60, Inscribed Angle Conjecture. And I know some of you like me when I put the name, and I usually don't. Inscribed Angle Conjecture. Which basically states the measure of an inscribed angle in a circle is, and here's the deal, the measure of this angle right here is not equal. Can you see that it's not equal to the measure of the central angle? It's not even close, is it? Remember, the central angle will have the same measure. Let's say that this is 72 degrees. It'll have the same measure as its intercepted arc, or the arc that goes with it. And I think that's pretty clear to most people. If it isn't, work with your friend, work with somebody at your table, draw a circle, draw a 90-degree angle with its center, a central angle with a measure of 90 degrees, and I think it'll be plain to see that the arc is also 90 degrees. So central angle has a measure that's equal to its intercepted arc and vice versa. And this inscribed angle, let's get back to purple. This inscribed angle has a measure that is half the measure of the central angle. So the measure of this angle is going to be, what's 72 divided by 2 is 36 degrees. 36 degrees. That's a well-written 36 degrees. Yay. So is equal, I don't want to put equal, that sounds doofy. And you can hear every word that I'm saying. Is half the measure of its central angle. And I'm going to put this in here. Okay? So that's the first conjecture. That's a fairly simple idea. I don't know how to get you guys to remember it. Some of you will mix them up. To me, it's pretty clear because the central angle clearly must be, or must have, the same measure as the intercepted arc, and then the inscribed angle is going to be less than that. How much less? Half. So, conjecture 61, which we call I'm not writing them down anymore. Writing on this thing's a pain, this app, rather than on my computer. So, inscribed angles intercepting arcs conjecture. So, if I have an inscribed angle here, this is a no-brainer, but an inscribed angle like this one, and you have a second inscribed angle, what color shall I choose? Such as this one. Inscribed angles, that's a C. Oh, stop it. You might not be able to see that. The app did something weird. Inscribed angles that intercept the same arc are. So what do you think? I would say I would think about it this way. I don't know if this is going to be red. Yeah, it's going to be red. I don't want it to be red. Look, if the purple angle intercepts this orange arc, it's going to be half of its measure, because the central angle is going to be equal to the measure of the arc, and the intercepted arc, or excuse me, the inscribed angle is half the measure of that central angle. Well, the blue inscribed angle is intercepting the same arc, which means it must be half of its measure as well, which means that the purple inscribed angle and the blue inscribed angle must therefore be congruent. And I wanted to change colors. Or the same measure. So they have to be congruent or they're the same measure. That's that one. And there's only 5 today, by the way. So, number 3. This one's kind of a no-brainer as well. Actually, many of these today are no-brainers. So, at least that's my opinion. If somebody's having a brain, you should get rid of it because it should be a no-brainer. Angles in a semicircle. Angles in a semicircle. Blank. So let's draw some. I keep going back to purple. Well, it's thinking I want to select because I held it too long. So if that is a diameter and I have a semicircle, if I draw an inscribed angle in that semicircle, and that's kind of what they're getting at with the language they used. What do you think is going to be the measure of that angle? Well, think about it this way if it's hard to see. That's an inscribed angle, and here's its intercepted arc. So what is its central angle? The central angle that goes with that arc is that one. That quote angle, you guys know I hate that. That angle is 180 degrees, so the measure of the inscribed angle must be 90. And that's no matter what. So let's draw a couple other ones so you can see this falling into place a little. If I draw it very extreme all the way over here and there, I'll get a 90-degree angle. If I draw it over here, over there, I get a 90-degree angle with my handwritten stumpy finger drawing. So angles in a semicircle are actually, I should correct that, shouldn't I? Are right angles. And it should be angles inscribed. So this should be inscribed. And we're not going to edit because I don't have time. Inscribed. So angles inscribed in a semicircle are right angles. Okay? That one's pretty straightforward, I think, as well. It's a no-brainer. Don't need to have it, but there it is. I believe the book has it because sometimes it's hard to see. It's hard to figure out that the black angle, for instance, is intercepting a semicircle. So 63. The blank angles of a, and this seems like a new word because it is, and because we have not called it this. It happens every year because we don't talk about it and the book has it written this way. I suppose I could write it another way, but I don't. Okay. The blank angles of a cyclic quadrilateral, and why did I plural it? Can I get just that tiny bit out? Yeah. The blank angles of a cyclic quadrilateral are what? Well, first of all, we have to figure out what in the heck is a cyclic quadrilateral. I'm talking too fast. Cyclic quadrilateral, if I draw it, maybe you guys will go, oh, wait, we know what that is. And then you can tell me what it's called. You can yell it at the screen. That is a cyclic quadrilateral. We would also call it an inscribed quadrilateral, or a, if we, well, that's good enough. Inscribed quadrilateral. So what are we talking about? The angles of a cyclic quadrilateral are what? So what angles? Opposite, adjacent, all? That doesn't make sense. The all angles. So let's do a little highlighting here. Let's look at this green. This green arc is being inscribed by this green angle, or intercepted by that inscribed angle. And then this blue arc is being intercepted by this inscribed angle. Well, what do you know about this inscribed angle? The blue one, for instance, or the green one, whichever one. Isn't it going to be half the measure of that arc? And the green one, the green inscribed angle, will be half the measure of its intercepted arc. So let's look at the blue one and call it A. Let's call the green one B. And won't A plus B equal 360 degrees? Because all the way around the circle, 360 degrees. But then this, let's just use black. This is going to be half the measure of A, so that's A over 2. And this is going to be half the measure of B, B over 2. So how do we write this out? If I divide everything by 2 in this equation, won't I get A over 2 plus B over 2 are equal to 180 degrees? So here it is. The opposite angles of a cyclic quadrilateral are, if they add up to 180, they will be supplementary. Or if you're Mr. Zuka, supplementary. He made fun of me Friday night. We were playing games. He says I say engine. E-N-G-I-N-E. Funny. He says it should be engine. And now I sound like I'm in elementary school. And here's the last one. Yeah, I'm a little punchy because I'm tired. Where are we at? Black pen. So this is the last conjecture, and then you can get started with the assignment, or what's left. 64. Parallel lines. I don't find this one particularly exciting, but it is definitely necessary. And, oh wait, I'm thinking of something else. Never mind. No, this one's pretty good. Intercept blank arcs on a circle. Notice how they say on a circle? Because the arcs are on the circle. So, parallel lines intercept. I didn't use the line tool yet. Does that look parallelish? Alright, so we're talking about these two arcs. Those two arcs. Parallel lines intercept blank arcs on a circle. I'm sure most of you already have the answer in your brain. And we're going to play around with this a little bit. If I draw this in and make what looks like a trapezoid, right? And then I draw diagonals of this trapezoid. Then I have this inscribed angle that intercepts this green arc, the one on the left. Then I have this one that intercepts this green arc on the right. Could we do a proof that would indicate these two angles as being congruent? So that would be a way to prove that the intercepted arcs are congruent. So parallel lines intercept congruent arcs on a circle. And that's it.